Okay, so now about the Cos inverse function. So we said that basically the domain of the Cos function is basically, since basically the Cos function is nothing but cos function by sine function, the sine function is 0 at the integral multiples of pi, and so we have to take those values out of the domain of the Cos function. So we can write the domain of the Cos function as all x is such that x belongs to R and x is not equal to n pi, where n belongs to the set of integers. And then the range of the function, of course, is R. So that means that the Cos function is not defined for the integral multiples of pi. So now if we restrict the domain of the cotangent function, for example, to 0 to pi, meaning that the Cos function, if you restrict the domain to 0 to pi, would be, for example, this is pi by 2, this is 0, and this is pi. This is basically one complete period of the function. The function goes from positive infinity to 0 to negative infinity. So if we do that, so if we restrict the domain of the cotangent function to the 0 to pi, then it's bijective with its range as R, basically, right? And in fact, the cotangent restricted to any of the intervals, for example, negative pi to 0, you can go from 0 to pi, you can go from, for example, pi to 2 pi, and etc. The function will be bijective and the range will be R, of course. And thus the cotangent inverse function can be defined as a function whose domain is the set of real numbers, and the range as any of the intervals that we discussed before. So these intervals give different branches of the function Cos inverse. So the function with the range 0 to pi is called the principal value branch of the function Cos inverse, and so you can say that the Cos inverse function is defined as basically the Cos function is defined as, you can say that the Cos function is defined as basically the domain of the function is R, and the codomain is basically 0 to pi, of course, not the open interval of 0 to pi. Now let me write down all of the things that I just said because they are important. So what we said is that basically if we restrict the domain of the cotangent function, the domain of the cotangent function to 0 to pi, then it is bijective, then it is bijective with its range as R, right? And the cotangent function, restricted to any of the intervals, for example, negative pi to 0, the open interval, and we are using the open intervals because we said that the cotangent function is not defined as integral multiples of pi, meaning that The function, of course, is not defined at negative pi. It's not defined at 0. It's not defined as pi, at 2 pi, and so on and so forth. So the cotangent function restricted to any of the intervals 0 to pi is negative pi to 0, or 0 to pi, or basically pi to 2 pi, or pi to 2 pi, etc., etc., is bijective with the range R, right? Thus the cotangent inverse function, thus the cotangent inverse function, meaning that the Cos inverse function can be defined as a function, whose domain is R, and the range could be any of the intervals, for example, negative pi to 0, or 0 to pi, or pi to 2 pi, or, for example, and etc. You can just keep going. And these intervals basically give different branches of the function, Cos inverse, right? And the function with the range, the function with the range 0 to pi is called the principal value branch of the function Cos inverse. Is called the principal value branch of the function Cos inverse. Now the function with and so we thus have basically Cos inverse is a function from the set R to the interval 0 to pi, the open interval 0 to pi. And now if you do the graph of these functions, what you will get is that f of x is equal to cot x, right? And if I draw the graph of the function f of x is equal to cot inverse of x, cot inverse of x, you can see that. And if I do the graph of the function f of x is equal to x, so you can see that basically we restricted the domain of this function to 0 to pi, meaning that essentially we have only this part of the function, right? Only this part of the function, and well, And well, this part of the function, as you can see, is let me take a look at this function. Now, as you can see, it's very interesting to note that basically you can see that this function, you see this part going up from here all the way up to this point, which is pi by 2 comma 0. Now this part of the function has been is of course that this is supposed to be the function that we get over here, which is the inverse function essentially. This line over here, this curved line over here, is supposed to be this is basically the two functions, or basically meaning that this part and this part are supposed to be symmetric about this line f of x is equal to x. And you can see that this part over here has essentially been reproduced, this part all the way up to here has essentially been reproduced over here with respect to this line over here, meaning that first of all we have the point pi by 2 comma 0, exchange the x and y coordinates, you will get 0 comma pi by 2, which is this point over here. And then each and every point on the graph of the function, you can see that, for example, you can see that this point will give you this point, 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 and so on. And so this part of the function that goes towards positive x's is actually the mirror of this part of the function that goes all the way up to goes towards the positive y's, right? And so what that means is that then this part over here is going to make the mirror the other part of the inverse function, which is this part over here. First of all, that we have the point pi by 2 comma 0, and pi by 2 comma 0, basically if you swap the x and y coordinates, you'll get 0 comma pi by 2, which gives you this point. And then, for example, this point mirror through the line gives you this point, this point mirror through the line gives you this point mirror through the line gives you this point, and so on and so forth, which is pretty interesting. So of course, but this is only the principal value branch of the Cos inverse function. Otherwise, the function would be something like this, meaning that the calculator has not, of course, given you the whole part. You would get a function like, essentially like this. Let me show you the picture here so that you see it. So you would get basically, you see that basically this is the principal value branch that the calculator also has calculated for us and has graphed for us. But then all of these parts would also be a part of the function, which of course we don't really care about that, because then if we have all of these lines all together in one graph, then of course that would not be a function in the first place, because then 1, 2 could be mapped to this point, and then could be mapped to this point also to this point, and so that would not be a function in the first place. That's basically why we restrict things so that we get only one branch of the function, and that is called the principal value branch of the function, right? So that is basically what we have here so far. Now in order to create a summary of everything that we did so far, let's create a table and create all of the information that we have had so far. So we said that basically we had all of these functions like the sine inverse, cos inverse, sine inverse, cos inverse, then we have the cosecant inverse, we have the secant inverse, we have the tan inverse, and we have the cot inverse functions, right? So these are the functions that we had. And so if I draw that basically, and then you have the domains and the ranges. So these are the domains of those functions. These are the domains of those functions. So you have the domains and ranges. So these are your functions. These are your domains. These are your ranges, right? And so for the sine inverse function, you can say that, so you have the sine inverse function, you have the cos inverse function, you have the cosecant inverse function, you have the secant inverse function, you have the tan inverse function, and you have the cot inverse function, right? So for the sine inverse function, we said that, well, of course, I'm not going to go through all of the functions one more time, because that would essentially take forever. But just to recap the whole thing, basically, if you have the sine function, let us calculate everything. If it's possible, let's see if that's actually possible. So if you have if f of x is equal to sine x, that will give you basically this function over here. So we said that we wanted to, that we restricted the domain of this function to negative pi by 2 to pi by 2. And if I then do the inverse of this function from negative pi by 2 to pi by 2, then that basically means that I have another line over here, f of x is equal to x, right? And if I do the f of x is equal to basically sine inverse of x, and as you can see, basically now that only the part which is basically so negative pi by 2 comma negative 1, here you have negative pi by 2 comma 1, and this point basically gives you negative 1 comma negative pi by 2, which is basically this point over here. Now this calculator is not very, so this is the sine function. Now if I draw the graph of the function f of x is equal to x, and if I draw the graph of the function f of x is equal to sine inverse of x, it's going to give me this function. And as you can see, basically the function, let me change the color if that's possible. That's actually not possible. Okay, so we had to restrict the domain of this function to negative pi by 2 to pi by 2, meaning that negative pi by 2 gives you basically that is negative pi by 2, and that is pi by 2. Now, since this function is going to be, basically the function is going to be a mirror image of the original function through the line basically f of x is equal to x, then basically, for example, negative pi by 2 comma negative 1 is going to give you, you have to swap the x and y basically coordinates negative 1 comma negative pi by 2, which is essentially this point over here, negative pi, negative 1 comma negative pi by 2. This point is going to be pi by 2 comma 1, and so it gives you basically 1 comma pi by 2. And then the rest of the function is going to build the rest of the graph for you, and you will get a graph like this. Meaning that basically the domain of the function goes from negative 1 to 1, and the range of the function goes from negative pi by 2 to pi by 2, right? So over here I can write basically the domain of the function goes from negative 1 to 1, and the range of the function goes from negative pi by 2 to pi by 2, right? So that is the first function that we have. The second function is the cos inverse function. The cos inverse function is essentially, so if I draw the graph of the cos function here, okay, so now the cos function, so basically we said that we could, basically this is 0, this is pi by 2, and this is pi, right? And I could, meaning that if I take, for example, if I were to go from negative pi by 2 to pi by 2, the function would not be 1, 1. If I go from 0 to pi, the function would be 1, 1. Meaning that I can actually restrict the domain of this function to 0 to pi, the function would be 1, 1 and onto, and therefore I could basically find the inverse of this function. Meaning that here I can write the f of or g of x is equal to cos inverse of x, and as you can see, now you can see that the range of the function goes from 0 to pi. The range of the function goes from 0 to pi, and the domain of the function goes from negative 1 to 1, right? So, and it's actually interesting to see that basically the original function, this point over here is 0 comma 1. Swap the x and y values, you will get 1 comma 0, which is basically this point over here. That gives you this point, and you see that the 2 points are symmetric about this line. And then if I get to this point over here, which is pi comma negative 1, swap the x and y values, you get negative 1 comma pi, which gives you this point over here. And you see that the 2 points are actually symmetric about the same line, right? So long story short, the domain goes from negative 1 to 1, the range goes from 0 to pi, right? So I can write over here that for the cos inverse function, the domain goes from negative 1 to 1, and the range goes from 0 to pi. Now for the cosecant inverse function, let's see what we had for the cosecant inverse function. If I draw the graph of the cosecant CSC of x, you can see that the function is, so you can see that basically I have this vertical asymptote. Of course, the calculator is not showing those asymptotes, but I have one asymptote here, which is at x is equal to 0, and now this is pi by 2, and this is at pi, I have another asymptote. And the reason for the asymptote is that, for example, sine f of x is equal to sine x, the sine function is not defined, is equal to 0 actually. The value of the sine function is 0 at pi, right? At pi, the value of the sine function is 0, and therefore you'll get an asymptote because then the cosecant function is not defined at that point, because the cosecant is nothing but 1 divided by sine x, right? So at all of these integral multiples of pi, you will get these asymptotes at 0, at pi, at 2 pi, at 3 pi, 4 pi, and negative pi, negative 2 pi, and so on and so forth. So what I can do is that I can take, so here what I can do is that I can take, so here I have basically this point is negative pi by 2 to negative 1, and this point is over here is pi by 2 comma 1, right? So I can restrict the domain of this function to negative pi by 2 to pi by 2, and then in that domain the function is actually basically 1, 1, and onto. Of course, there is a problem here, and the problem is that there's a problem here, and the problem is that the function is not defined at this x is equal to 0. So you have to take that out, right? Which means that you take that out, and that becomes the basically the range of the cosecant inverse function. So from negative 1 to from negative pi by 2 to pi by 2, and except for 0, that becomes basically the range of the that is actually the domain of this function. But then when you calculate, when you define the inverse of this function, or the cosecant inverse function, that becomes actually the range of that function. And then as you can see, the range of this function, as you can see, goes from negative infinity, is basically all the real numbers except for all the numbers between basically between 1 and between negative 1 and 1, and that becomes also the domain of the cosecant inverse function, which means that basically if I graph the function f of or g of x, if I graph the function g of x is equal to C inverse of x, you see that it gives me this function here, and this is actually the main branch of the function. I still cannot remember the term. It's the principal value branch of the function. This is only the principal value branch of the function. The calculator doesn't give you more of those branches, or all of the branches that you would get. And then what happens is that basically this point over here is pi by 2 comma 1, right? Swap the x and y basically coordinates. It gives you basically 1 comma pi by 2. And 1 comma pi by 2 is basically this point over here, and you can see that the 2 points are actually symmetric about the line y is equal to x. And then every other point is going to create other points of this graph, and so on and so forth. Meaning that, for example, this point goes through this line and then gives you this point. This point goes through this line, gives you this point, and so on and so forth. And moreover, this point over here, negative pi by 2, and this point are symmetric about the line, and then the function is, and then the rest of the function right here is going to give you the rest of this graph, and then the graph is going to be basically the graph of the function f of x is equal to cosecant inverse of x, which means that basically you can say that you can simply take the domain of the domain of the cosecant inverse function. We said that we would basically restrict the domain of the function to negative pi by 2 to pi by 2, and we had to take out 0. So that becomes the range of the cosecant inverse function. And as you can see, basically the function over here goes from negative pi by 2. The y coordinate is negative pi by 2. The y coordinate here is pi by 2, and y is actually an asymptote here. So y has been taken out. So that means that the range of this function is now, negative pi by 2 to pi by 2, negative pi by 2 to pi by 2, and that, of course, we have to exclude from that the set containing 0, right? Moreover, over here we said that basically the function, since we wanted to determine the domain of this function, the cosecant inverse, we have to go for the range of the original function. The range of the original function is r minus basically all of these values between negative 1 and 1, which means that here you get r minus basically all of these values, all of the basically the open interval negative 1 comma 1. Okay, so that's about the cosecant inverse function. Now about the secant inverse function, of course I can copy all of the values from that table to this table, but I mean, practice, well, is always a good thing. So, not of course always, but sometimes it's necessary, of course. Now the secant inverse function, now if I CSC of, I don't know if that is actually the right way of CSC, yes, no, secant, okay. So the secant of x is basically this function, and we said that we could basically restrict the domain of this function to 0 to, you see, this is basically 0, and this is pi, right? So we can restrict the domain of this function to basically 0 to pi, and of course the function is not defined at pi by 2, because as you can see, the secant function is 1 by cos function, and the cos function is you see over here the secant function is basically the secant x is 1 divided by cos x, of course, and the cos of x is basically is of course 0 at pi by 2. When at pi by 2, basically you know that cos of pi by 2 is equal to 0, meaning that at pi by 2 the secant function is not defined, meaning that so somewhere over here, as you can see, you would have an asymptote which is not drawn here, of course, by this calculator, and so we can basically restrict the domain of this function to 0 to pi, and of course we have to take out pi by 2 because the function is not defined at pi by 2, and that becomes the range of the secant inverse function. That becomes the range of the secant inverse function. So 0 to pi and take out pi by 2. 0 to pi, the range becomes 0 to pi, and we have to take out pi by 2, right? That is the range of the function. Now, the domain of the domain of this function is going to be the range of the original function. The range of the original function, as you can see, goes from negative infinity all the way up to positive infinity, but again these values between negative 1 and 1 are not included. So I have to write here r minus basically the interval negative 1 comma 1, right? And now if I draw the graph of if I graph basically f g of x, for example, is equal to g of x is equal to secant inverse x is equal to secant inverse of x. As you can see, over here we said that the domain of the function is r minus negative 1 to 1. So the domain is r, so that you can see that the domain goes from r to r, and over here this is negative 1 and this is positive 1, so all of these values are excluded. And the range of the function goes from basically 0 to pi, so this must be pi over here, so 0 to pi, except for basically pi by 2, which is basically not a part of the function here. So you can see that this is actually pretty magical, and it's taken human beings like about at least 2,000–3,000 years to get here, and even a few years ago, like for example 10–12 years ago, when I was going to college, there was no such thing as a graphing calculator on a computer that you can just simply using a keyboard enter everything that you wanted into the calculator, and the calculator in just a fraction of a second gives you over the internet. The software is written all over the internet on some server, and the server gets your query and then sends you back the function. Back then there were these handheld calculators, and you had to enter your function into that calculator, and it took you like years in order to just learn how to work with that calculator. It was not easy, really. It was really hard to work with those calculators. And then, of course, the calculator had some sort of a 2-inch, 3-inch, for example, not even an LCD. It was something like a matrix screen, dot screen, or something like that, and it would give you some sort of something that you could probably call a graph. There was no, basically, you can see that I can move this function around, I can zoom in, I can zoom out, I can do anything I want to do here. All of these things were simply actually not possible back then, and it was just simply not there. The software was not there. The browsers were not even nearly capable to do any such thing as in this category. Okay, so we have a couple more things here to cover. Basically, there is only the tan inverse and the cot inverse. We will cover these two as well in this video. Okay, so now basically there is 2 of these left, so let's get these done as well. So basically we said that the tan function is basically it was the sine function divided by the cos function, right? And so the tan function, tan of x is equal to basically sine x divided by cos x, which means that whenever cos x is 0, tan is not defined, which means that at pi by 2 and 3 pi by 2, so at the basically odd multiples of pi by 2 tan is not defined, which means that basically if you draw the graph of the function, now if I over here, if I have basically tan f of x is equal to tan x, you can see that at pi by 2 the function is not defined again at so this is 0, this is about pi by 2, this is pi, right? At pi the function goes to 0, at 3 pi by 2 again the function is not defined, and so on and so forth. So that means that we can get, actually we can take actually the, I think we took the domain of the function as negative pi by 2 to pi by 2 if I'm not mistaken, yes, from negative pi by 2 to pi by 2, and so negative pi by 2 to pi by 2 becomes the range of the tan inverse function, because that's the domain of this function, right? So negative pi by 2 to pi by 2 becomes the range of this function, negative pi by 2 to pi by 2, and so basically that is the range of that function. And well, you can see that basically the range of this function is R, so therefore the domain of the tan inverse function becomes R, meaning that over here you will have R. And this is the closed interval of negative pi by 2 to pi by 2. Actually, this is not the closed interval because basically the tan function is actually not basically defined at negative pi by 2 and pi by 2. Only between pi by 2 and negative pi by 2 it's defined. And of course, if you do the graph of the function, you will get something like this: tan inverse of x, which is basically this function that you get here, and this function is actually is symmetric about basically this part of the function, and this inverse function are symmetric about the line y is equal to x, right? Now about the cot function, we said that basically the cot function is basically cos x by sine x, meaning that wherever sine is 0, the cot function is not defined. Sine is 0 at integral multiples of pi, meaning at 0 pi, 2 pi, 3 pi, and so on and so forth. So that means that, for example, at 0 the function is not defined, at this is pi by 2, at pi is not defined, at 3 pi by 2 you have some output, at 2 pi you don't have any outputs, and so on and so forth, right? So what I can do is that I can take the domain of this, restrict the domain of this function to 0 to pi. Between 0 to pi the function is 1, 1 and onto. So if I do so, then 0 to pi becomes the range of the cot inverse function. So then I can write the range as 0 to pi. At 0 to pi, and let me see if that actually works. Yes. Okay. So this is the closed interval of 0 to pi, and actually at 0 and pi, of course the function is not again defined, so I cannot do this. I have to use the open interval of the because at 0, for example, sine 0 is equal to 0, then the cot function would simply not be defined, right? And then what happens is that basically the domain of this function, or I'm sorry, the range of this function goes from negative infinity to infinity, which is R, which becomes ultimately the domain of the cot inverse function. So the domain of the cot inverse function becomes R. And so if you draw the graph of this function, cot inverse of x, the cot inverse of x, you will get basically this function. You will get this function over here, which is, and as you can see that the two functions are basically this part of the function and this part of the function, and this inverse function are symmetric about this line y is equal to x. So that's basically that is basically all that we have here. So this, of course, this table is useful because we cannot, I mean, it's not, sometimes, of course, you can do that, but it's more convenient to have this table and use it at least throughout this chapter, but wherever you happen to be thinking about such things like the domain and the range of the basically of these functions, then you can, of course, if you have to, you can derive that. Otherwise, you can use the same table that we have prepared here. Now, there is a couple of things that we need to, there is a couple of notes that we have here. Now, basically we said that if you have f of x is equal to sine x, the inverse of this function, f inverse of x, would be sine inverse of x, or you can write it also as sine inverse of x, right? Now, basically this sine inverse of x is actually the inverse of the function sine x. But you can also come across the notation sine x whole inverse. What this means is that this is the same thing as basically 1 over sine x, right? That is the meaning of basically sine x whole inverse is 1 over sine x. These are not the same thing. And basically this applies to other trigonometric functions. For example, if you have, for example, f of x is equal to cos x, then the inverse of this function would be cos inverse x. And if you write, for example, if you write cos x whole inverse, is the same thing as 1 over cos x. And so on and so forth for all of these, for all of the trigonometric ratios or functions that we have. That is that. Moreover, whenever no branch of an inverse trigonometric function is mentioned, we mean the principal value branch of that function. So basically, whenever, for example, you write, for example, the sine inverse function, the sine inverse of x, what you mean by this is basically the definition that we have for the sine inverse function, meaning that you mean the principal value branch of the function and not any other branch. If you mean to use any other branch, then of course you have to specify that through words or notation or something like that. And the value of an inverse trigonometric function, which lies in the range of the in the range of principal branch is called the principal value of that inverse trigonometric function. So it says that the value of an inverse trigonometric function which lies in the range of the principal branch is called the principal value of that inverse trigonometric function. This is actually important. So the value of an inverse trigonometric function, or you can say the values of an inverse trigonometric function which lie in the range of the range of the principal branch, is called the principal values, or are called the principal values of that inverse trigonometric function. Of that inverse trigonometric function. So what that means is that, for example, let's say that you have the inverse trigonometric function, for example, the cot inverse x. The cot inverse x is basically if I were to give you an example, a good example here, so this is the cot function, right? Now, let me actually save this somewhere over here. Save it on desktop. Inverse trigonometric functions, domain and range, right? Domain range table. Okay. Now, if I were to, what I think that means is that, see over here, if I suppose that I have this is the cot function, right? So the cot function is basically the cot function basically behaves like this, and the inverse of the cot function eventually becomes some function like this, which of course the principal value branch, the principal value branch of that function becomes basically this branch over here. Now, you know that basically from the table that we prepared, you know that these values go from 0 to pi. These values go from 0 to pi, of course excluding 0 and excluding pi, right? So now what this note is saying here is that the value of, actually the wording is not very proper, but what I think that means is that the values of an inverse trigonometric function which lie in the range of the principal branch. So this is the range of the principal branch, which goes from 0 to pi. Of course, again, excluding 0, excluding pi. Those values are called the principal values inverse trigonometric function, meaning that I can say that the principal values of the inverse trigonometric function cot x, for example, cot inverse x actually, the principal values are 0 to pi. 0 to pi. These are the principal values of principal values of this function. That's what I think that means. Unless we find out that what basically the meaning is something else, which we will find out in the exercise. Otherwise, most probably it's the meaning there. And then you can of course do the same thing, meaning that, for example, this function can give you, depending on how you define your function, meaning how you restrict the domain of the function, you will get one of these branches over here. And then, as you can see, the range of the function goes either from pi to 2 pi or negative pi to 0, or for example I don't know, some value pi units before pi to negative pi, and so on and so forth, right? Which means that basically you could essentially get all of those values for this function. But the principal values of this inverse trigonometric function are 0 to pi, as far as we know. Yeah. Okay. So I'm going to end this video here. In the next video, we will talk a little bit about a couple of exercises. So I'll see you in the next video. Thank you.